Hi, I'm Hogon. Today I'm going to review the BJT. BJT means bipolar junction transistor. Comparing with MOSFET, MOSFET was unipolar junction transistor because on NFET we only handle about the electron, and on PFET we only handle about the holes. But in this BJT we are gonna treat both electrons and holes. That's why the driving current will be very higher than MOSFET. So let's start. First, we have to know the structure of this BJT. We have three parts: emitter, base, and collector. And there are two types of BJT. One is NPN transistor, another one is PNP transistor. And in circuit, we're gonna use the symbol of this. We always put the direction mark on the emitter side. If the direction marks points from base to emitter, we'll call it NPN transistor. And if the mark points from emitter to base, we'll call it PNP transistor. The difference between FET and BJT is that on MOSFET we had to control the channel by putting gate bias on the gate side, and it was capacitively coupled to the channel, and the drain current flowed by drift. But in this BJT, the base is made by direct connection with the emitter and collector, and this current flows at least in part by diffusion. And by KVL, we learned that VC, the voltage between collector and emitter, equals to the sum of the VCB and VCBE. And by KCL, we learned that the current flow through the emitter equals to the sum of the current flows through the collector and base. So, and also we learned that we learned two parameters. There are alpha and beta, which is common base gain and common emitter gain. Common base gain means that we're gonna put the ground level on the base. So, and comparing the current flow through the collector and base, we're gonna compare it. So we can determine the efficiency. So the alpha equals to the IC over IE, and its value is normally very close to 1, but not greater than 1. But yeah. And common emitter gain is also, we're gonna put the ground on the emitter, and we're gonna compare the IC and IB. So beta is equal to IC over IB, and its value is normally around 100. And we also learned about the operation modes of BJT. We separated by two junctions. One is EBJ, which is emitter base junction, and CBJ, collector base junction. If there are reverse bias on both EBJ and CBJ, we call it cutoff mode, which means this device is not working. The switch is off. And if there is forward bias on EBJ and reverse bias on CBJ, we'll call it active mode, which means this device is working on active mode. And if there is a forward bias on both EBJ and CBJ, we're going to call it voltage saturation. And we also learned about IC and VC curve. It is very similar with ID-VD curve on MOSFET, but the difference is, the linear region and saturation region is opposite. And we call here the very high increment of the curve. We call this voltage saturation, and when this curve goes constantly, we will call it forward active region. Yeah, and we also learned about DC load line. With this IC-VC curve, we are gonna put the resistive load line, and on certain intersection points, this device is working. So our conclusion was that, if this device is on cutoff mode, there will be no current flowing, and VCE will very large, and if the device is on saturation mode, the base current will be very large and VC is very low, and also output current IC will be very large. And on forward active mode, the output current was very proportional to the base current, and output voltage was inversely proportional to the base current. And we also studied about the Miller effect. By comparing the input and output impedance, we could know that the input capacitance increases by feedback capacitance. And we learned this common base and common emitter gain in order to know the current gain. If you know alpha, we can find out beta and vice versa. Beta equals to alpha over 1 minus alpha, and alpha equals to beta over 1 plus beta. And also, we learned about current gain. In order to find out the value of the alpha, we learned about 3 parameters. One is injection efficiency, and another one is transport efficiency, and lastly collection efficiency. And on the second class, we learned that how can we manufacture this device to make very good current gain. We learned that we had to make the base width very thinly, and we had to use very highly doped emitter. But in real device, we couldn't make them like that because of the band gap narrowing. If you dope emitter too much, the barrier energy level between emitter and base will gonna be very higher than before, so the electron from emitter cannot move to the base level easily, so the carrier supplying will be very poor than before on emitter. That's why we couldn't make it how we want. And we also learned that graded base transistor and drift transistor using doping gradient and using heterojunction. Thank you.